full disk of Jupiter taken with the wide field camera in a blue filter. The wavelength is 410 nanometers. And you see on the left a blow-up of the impact site. It's expanded and enhanced so you can see it. It's very dark. We have wavelengths ranging from 3,036 nanometers out to 956 nanometers. We don't have those all ready to show you now because we obviously haven't had enough time to do that. But I'd like to describe for you what it looks like. At all wavelengths except a methane band, it looks like this. It's dark, and it has this dark material to the south. In the methane band image, the wavelength is 889 nanometers. Everything that you see as dark there is bright. It's completely inverted. Looks like a negative image. We don't fully understand what we're seeing here yet. We don't have ready for you yet images that were taken in the previous orbit. In that orbit, what we could see at all wavelengths was what looked like a plume on the limb of the planet, and then we saw the plume flatten as if it was spreading out, and that was all we saw. We detected it at all those wavelengths, though. And so we'll be working throughout the night to get these data ready to show to you tomorrow morning. I would now like to show you a video. If any of you are not convinced that this is from this comet, I would like to show you a video of what Jupiter looked like yesterday. And this is brand new preliminary data, and it's in a fairly raw format, so you'll see seams and colors that if we had had more than 18 hours, we would have done a prettier job. But I wanted you to see the quality of imaging that we're getting from the Hubble Space Telescope. So if we could run that video, please. It was created by Eric DeYoung based on 6 orbits of data yesterday afternoon. And I hope we have the video.
Can you roll the video, please? Okay, it's going out on the satellite. We'll have it here shortly.
Okay. This will basically take 5 different images of Hubble, and what we have done is map project them and then recombine them to make basically a sphere. I hope we do get to see it. Well, while they're working on that, let me just show you the geometry of this impact in case some of you are a little bit confused, because that's a very confusing image. If this is Jupiter and you're all on the Earth, you're looking this way, okay? Jupiter's spinning like this, okay? These impacts, this train of comets, nuclei, are coming in from the bottom at about an angle something like this. And you can't see them happen. All right? There we go. Let's take a quick look at the video. This is a very rough reconstruction, but you can see the amazing quality of the images from the wide field camera. And there is the site. It's going to stop on the right longitude so you can see the pre-impact view. There's the great red spot and a white oval. This is the wide field camera. With the planetary camera, we're going to get even better resolution. And we'll, of course, we'll have a little bit of time to clean this up, and it'll be a really nice video when we get that chance. Okay, that's the view, very similar, not quite exactly the same, but similar to the impact site. You see the great red spot, and you see that little white plume off to the side, just below and to the left. And if we could go back to the other one, I don't know if that's possible or not. Yes, we can. We'll look again for the great red spot and that white spot, and you'll see where the little black thing is next to it, the impact site. Well, we're going back. A little bit of dead time. Okay, in the meantime, while they're working on that, continue my story here. All right. You could not see the impacts occurring, although the Galileo spacecraft, you'll all remember, is in a perfect view to get some good pictures of that. And so that will be fascinating to see. Here we go. See the great red spot? See the little white oval? And now further on you see that black splotch. It was not there the day before. It's a new feature on Jupiter, and we're going to have 20 more of them, even brighter. It's going to be a great week. So I think I'll stop there and let the rest of my team have some time to talk.
Okay, I'd like to go ahead and introduce the other.
Q2. Q1 is the bottom where the figures on the right.
Good afternoon. I'm Don Savage, Public Affairs Officer for the Office of Space Science. And welcome today to the Goddard Space Flight Center and the latest of our Comet update briefings here at Goddard. Today we have a major announcement to make, major discovery by the Hubble. And our top news this morning, we will also have Dr. Rene Pronget, who will tell us about how cometary debris is making the Jovian aurora light up. And Dr. Lucy McFadden will give us a worldwide wrap-up, and Dave Levy will be here for discussions on the observing. I'd like to go ahead and introduce our panel right now. To my left, Dr. Roger Yell with the University of Arizona. He's a scientist from the University of Arizona and a member of the Hubble Space Telescope spectroscopy team. To his left, Dr. Rene Pronget from the Institut Astrophysique Spatiale in Orsay, France. She's a scientist from the French Institute at Orsay and a member of the HST Upper Atmosphere Imaging Team. In the center, to her left, Dr. Steve Marin, our moderator for today. He's a senior staff scientist at the Goddard Space Flight Center. To his left, Dr. Lucy McFadden, University of Maryland and University of California, a visiting professor at the University of Maryland and coordinator of the Worldwide Comet Observing Campaign. And to her left, David Levy, co-discoverer of the comet and longtime comet observer. Welcome, panelists. I'd like to turn it over to you, Steve.
Thank you, Don. Good morning, ladies and gentlemen. For those of you who had the advanced schedule, I'm not Eugene ShoeMaker, and I won't have any explosive results for you. It is a pleasure to be here again. I've lost count of all these fragments, but fragment P2 should have struck within the past hour. And as I think you all know, many of you led with it yesterday or this morning, the first of the three other big fragments, the Q, R, and S, that will be hitting Jupiter at intervals of approximately equal to its 10-hour rotation period, so they'll hit at nearly the same spot at 10-hour intervals. That will start at about 3:32 Eastern Daylight this afternoon. We'll hear a little bit more about that later. Now for this, what I personally as an astronomer think is a very exciting scientific result to emerge from ShoeMaker-Levy. There's more to it than just a big show. We're fortunate to have Roger Yell at the University of Arizona tell us about this Hubble spectroscopy result.
Well, good morning. And as you all know, there's two sorts of information that the Hubble Space Telescope's been gathering. What you've seen mostly is images where you see the entire planet and the impact site at a very specific color, a specific wavelength. But also with the spectrographs, we look at one spot on the planet, but look at all the colors, all the wavelengths simultaneously, and that's what we call spectroscopy. So I'm going to report on some spectroscopy results. You can see on the monitor, I believe, an image of the G impact site, and it's the spectroscopy from the G impact site. We knew that was going to be a big one, so we pointed the spectrograph there several hours after the impact. And in the next, could we have the next graphic, please? The arrow is pointing to the location of where our spectra were obtained.
Spectrograph was the faint object spectrograph.
Faint object spectrograph. That's right. I don't know how to get that on the screen.
Next graphic, please. They'll have it up in a moment.
Okay, and what we're going to see in this graphic is the distribution of brightness from this spot as a function of wavelength or color. Now, different molecules, okay, there it is, and I'm going to be talking about.
That's ultraviolet light.
This is ultraviolet light. The wavelength is probably hard to read off that scale, off the image there, but it goes from about 150 nanometers to 3,000 nanometers. So this is light that doesn't get transmitted through the Earth's atmosphere. You need to be above the Earth's atmosphere to observe it, and that's why we use the Hubble faint object spectrograph to make these measurements. So what we see there is the ratio of the light from Jupiter after the impact to the light from Jupiter before the impact. And you can see that the ratio is not 1, which tells us right away that something's changed. It's less than 1.
If it were 1, it would be a straight line, right?
If it were 1, it would be a straight line across the top of that image. It somewhere varies from about 0.2 to, I guess, 0.7. So what that tells us is that these spots are darker in the UV after the impact than they were before, and we knew that already from the images. It's no surprise. But if you look very carefully at distribution with light with wavelength, you can look for molecules. Molecules will absorb at specific wavelengths, specific colors that are their own signature. So one molecule will absorb at one wavelength, another molecule will absorb at another wavelength, and by analyzing this, you can identify some molecules. Yesterday, Keith Knoll told you about ammonia, which happens to absorb light right around 2,000 angstroms, which is the minimum in that spectrum there. And there's ripples there. If you look carefully, you can see ripples in the spectrum, which are characteristic of ammonia. What he didn't show you yesterday were the larger ripples to the right at about 270 nanometers. They're about, well, I think they're fairly obvious there. It looks sort of like fish bones or something. And that was very exciting when we saw that yesterday, but we had no idea what it was. And so we spent the last 48 hours or so trying to figure out what this molecule was. And it was something of a mystery. There are a few clues that that we went by in the spectrum. First of all, it's a very regular spacing of ripples in that, and that tells you that it's a simple molecule. Secondly, the ripples are close together, and that tells you that it's a heavy molecule. So armed with that, that eliminates some number of molecules in the universe. But I should have said, first of all, that we had expectations about what we were going to see. We knew what molecules to look for and where to look for them, and we didn't see those. We saw ammonia, which was expected, but this is something that was totally unexpected, so we didn't recognize it right away. We had to go off and search spectra of all the molecules that we could think of to find out what this was, and none of the simple ones matched up. So we got more and more perplexed and kept looking. But as I said, we had these clues. It's heavy and it's simple. And finally, about 3 o'clock in the morning, we started zeroing in on sulfur. And in fact, those features are a very good match to the spectrum of sulfur, sulfur gas, S2, the S2 molecule.
Sometimes called the dimer, the two similar molecules, two similar atoms in the same molecule.
No, it's not.
Can't get them all.
It's a diatomic molecule. It's anyway. So that's a definite detection of S2 molecule in the atmosphere of Jupiter. Now, also there's some more structure around. In addition to ammonia at the shorter wavelengths where that big minimum is, and by looking carefully at that, we think that there's probably some hydrogen sulfide, H2S, in the spectrum at that location. That's not as clear-cut as the S2, but nevertheless...
Because we haven't had a lot of news in that area, has to do with the effects involving the magnetic field of Jupiter and the interaction with the comet. And Dr. René Pranget from the Institut d'Astrophysique Spatiale in Orsay, who can pronounce all those words much better than I, is involved in the Hubble imaging team working on these problems. And tell us what you've been learning.
Okay. It's right that one of our major interests in the observation, on top of studying the upper atmosphere of Jupiter, was to understand the physics at work in the magnetosphere. And since the magnetosphere is not a trivial object, I will just briefly put it into context before I discuss the observations. Jupiter, like the Earth, is a very strong magnet, and the magnetic field lines delineate a cavity in the solar wind, where a lot of plasma, which plasma in our jargon is a tenuous ionized gas of electrons and ions, are confined. This cavity is very extended. It's millions of kilometers in diameter. It's 5 times the sun. And the tails extends still farther. At times it goes up or down, as you would like, to Saturn, which is 5 astronomical units. So the magnetosphere of any magnetous planet is a huge natural laboratory for plasma physics, and that's why we're interested in that. Unlike the atmosphere that you have seen a lot in the last few days, the magnetosphere of Jupiter is not visible, practically invisible at all wavelengths, except in the decimetric radio wavelength, which has been used to discover the magnetic field of Jupiter. So we can only study the magnetosphere by deep space mission in situ measurements or by monitoring remotely the auroral emissions. And that's why we are interested in that. The aurorae, that again are like the aurorae on Earth, which are also become polar lights, they are at the end of the chain of processes in the magnetosphere. It's at the place where energetic charged particles, so electrons and ions, finally fall, and we say precipitate on the top of the upper atmosphere. And the energy of the collision of these particles on the constituent species of the atmosphere makes the atmosphere shine, either in the UV or in the infrared, not in the visible spectrum. And you can see on this picture, which is on top, which is an image of the WIFPIC 2 camera, around below 2000 angstrom in the far ultraviolet. So it's not visible just by naked eyes. On both sides, in the polar region, north and south, you can see these lights, kinds of ovals with spots, which are the footprint of magnetic field lines which go far away in the magnetosphere of Jupiter, and where the particles which are along these magnetic field lines, they fall down and they impact the atmosphere, they make it shine. For us, it's a signature of what happens in the magnetosphere. We have been using two cameras. We have been using the WIFPIC 2, which is the American camera. We have been also using the faint object camera, which is the European camera on board HST. This is an image which has been taken on July 13, before the impact, 2 days before the first impact. And already 1 week after the first dust, sufficient dust was inside the magnetosphere that we could expect some effect from the dust with the plasma in the magnetosphere. There had been a lot of prediction of what could happen in the magnetosphere. Some effects could come from the dust in the leading edge. Some could come from the comet of the comet itself, interfering with the plasma in the magnetosphere. And we could expect to see some effect even before, like precursors of the impact. In this image, you can see also the North Pole, the South Pole. We cannot see the whole...
Can we have that graphic back, please?
So we cannot have the whole planet because the field of view of the faint object camera is much smaller than the field of view of the WIFPIC 2. But the interest of the faint object camera is that you have a very, very good spatial resolution. You can get very faint details, so they are very complementary. And on this graphic, you can see what we are somewhat frustrated because we didn't see anything spectacular before the impact. We already had images of the aurora. They looked like that, except that the North Aurora consistently looked somewhat fainter, maybe at times much fainter than usual. And it looked fainter than the South Aurora, which is this nice necklace on the lower panel. We got the same kind of result with IUV. We have been monitoring the aurora with IUV for several weeks already, and we found that the North Aurora was weaker. We cannot tell why. We cannot understand that. We expected, if any fainting, we expected it in the south, because the dust could be inhibiting the processes which give rise to the aurora. We get it faint in the north. Maybe it's just coincidence, but we have to.
But maybe it's brighter. Couldn't it be brighter in the south and it's being enhanced by the dust from the comet fragments?
Oh, it's clearly fainter in the north. We have a lot of trouble getting the north.
Okay.
Normally, you can see an oval, which is around, you have a spot in the middle. This is very, very obvious in all the data.
And you find this both with the Hubble telescope and with the International Ultraviolet Explorer.
Right, with both. So we can tell for sure it's an effect of the comet, but it may be an effect, a general global effect of the dust in the magnetosphere. Then we got this nice image on July, 2 days ago, was it July 18?
Yes.
With a WIFPIC 2 that I hope we'll get here on the screen.
Next graphic, please.
And you can compare this image to the one we got before. You can see the aurora on top, the north. It's still fainter. You can see the left edge. You can see the aurora on the south. And below the north auroral oval, you have two bright spots, which are very low for us. It's very low latitude. It's totally unusual. It was not unexpected. I can tell there had been predictions that maybe the comet plasma could be ionized. This could drive a current, and it could enhance create new.
Okay, so the two bright spots you're talking about are the upper left and
the upper left, on just at the footprints of this new magnetic field lines which have been drawn now. Oh. And this is quite new. We never saw that. We never saw any aura below what is the one you have seen on the previous two graphics.
So that's, to make sure I understand what you're proposing, you think that material from the south pole where the fragments are impacting might be drawn through the magnetic field lines up to the north pole?
Right, that's what I'm thinking.
Wow.
There have been, well, if you look back to the prediction that has been made, it's clear that we expected some effect of the ionized plasma in the material in the comet to interact with the plasma in the magnetosphere. But we didn't know what we would do. And in any case, we expected to get something in the south, not in the north. And we worked out a lot to get the possibility to have closed field lines, because the magnetosphere, at times, the field lines, they're open to the solar wind. So in that case, something which happened in the south do not have any counterpart in the other hemisphere. So we worked the geometry so that we can get a closed field line with a footprint in the north, visible also from Earth.
So the north and south are connected by the magnetic
in
field.
that case, they're connected. They're connected, and on top of that, the footprint of the north is in front of, because the field line is distorted in the meridional plane. So you can see the footprint in the south. It's just right at the limb, but you can see it's already 30 or 40 degrees on the limb
If you think
from the limb on the north.
if you imagine it's kind of a bar magnet inside Jupiter that is responsible for magnetic field, in that model, then the bar is off-center and tilted.
Off the center, tilted,
And that's why it can be in
bent
back.
and
These lines can be in back on the
Right.
south and in front on the north.
so we are lucky. Well, not only lucky, we worked it out. And we get this bright spot in the north, but we have nothing in the and we didn't get anything, except maybe you can see something very, very faint and diffuse at the footprint of the
On the
larger,
south.
in the south, of the larger field line. We cannot tell, well, that's probably not precipitation of particles. We do not know what it is. It may be related. But this on the north pole, it's necessarily energetic particles. So something happened. Some material from the from the comet itself was liberated in the south pole, accelerated by some way along these magnetic field lines, and fell into the northern hemisphere, like an iron gun, in fact.
Now, Renee, would these be visible in visible light where our eyes are sensitive?
It's far ultraviolet. The auroral emission, I mean, the emission collisionally excited in the atmosphere of Jupiter, they cannot be seen in the visible, only in the ultraviolet from it depends on the composition of the atmosphere. On Earth it's visible. On Jupiter it's mainly from hydrogen or for hydrocarbons. And it's either ultraviolet or infrared. Unfortunately, we cannot see them in the visible. So that's a major, I think it's a major discovery. We have to understand what happens. We have two options so far. Maybe there are other options open, but we thought of two. Either the material was liberated after impact, and we got it along the field lines, and we see it in the north, and that's why we do not see anything in the south. Or another possibility, which was predicted, in fact, and I think I should send an email to Dr. Wing-Ip. We have published a paper very short ago, telling that within 1 Jovian radius, we have the conditions so that the coma entering before impact could create a current along the field lines, which would give the condition for such an effect to appear.
So you have to do more than just throw stuff up from the impact. You have to have an electrical or magnetic process that accelerates these electrified particles and drives them up the magnetic field line.
You have to get like an electric circuit, and then you have to have like kilovolts of potential drops to accelerate the particle to high energy.
Thousands of volts.
Thousands of volts to accelerate the particles. So it's not an easy process, and we have to work on that. And it's a lot of modeling probably, and we learn a lot about the plasma physics in general and Jupiter in particular.
Great. Thank you, Dr. Pranger. I think these are two really fascinating findings from the Hubble telescope, and we had an assist from the IUE. I'm sure we'll be hearing more about IUE as the week goes on.